So today I'm just going to start off with just a quick thing, and this is for you guys who are doing the salt tracer test on Friday. One of the things I wanted to highlight was when we're doing these types of advection flow models and stuff, when we're going to dump salt into a ground and we want to figure out if we're going to see it. Well, one of the things we have to do is figure out how much we're going to put in and then how much are we going to get out so we can read it on our instrument. We don't want it to be so dilute that we can't see it. We don't want it so high that, the salt is so dense that it just sinks. So this is just to give you guys an example of, and this is using one of the papers that we read, one of Madison's papers where they were looking at the salt concentrations in it. In the field. So one of the things that we looked at is, like if we're pumping out of a well and we want the final concentration to be 6 millisiemens per centimeter. That's what electrical conductivity comes out of. That's 6,000 microsiemens. But we know that the background water is about 600 in there. Well, one of the things we can do is if we use that equation from that paper that we read with Madison, well, they were saying that chloride in milligrams per liter equals 0.33 times the electrical conductivity in microsiemens per centimeter, which equals about 2 grams per liter of chloride. Well, if we assume that the mass, well, we're not going to assume anything, but we know that the mass of sodium chloride is 60.33% chloride and 39.33% sodium. If we take that 60.33 and we rearrange this equation, because what we want to know is 60% of what equals 1.98, because that's what we want our final concentration to be, because we want our number at the end to work out to be the 6,000. It works out to be 3.28 grams per liter of sodium chloride. Well, if we assume that the water is flowing at 5 gallons per minute, which is 18.9 liters per minute, we look at this at 3.28 grams per liter equals 61.9 grams per minute. Okay, so we need to inject 61.9 grams per minute of salt. Well, say if we're going to inject for 15 minutes at that 61.9 grams per minute times 15 minutes equals about 928.5 grams. And that's about one of those little containers of salt that, you buy, the Morton salt, that costs like $1 over at Schnucks. You take one of those and you have 15 minutes to get it into the water. Well, what we're going to do is we're going to take this 1 carton of salt, mix it with a couple gallons of water, and then pump it in over a 15-minute period of time, and we will get that full concentration of salt over 15 minutes. So we want the final concentration so that when we get our breakthrough curve, this up in here is equaling that. So that's what we're going to be trying to do with this. And so we can see it because we know what our background is, and we want to have this as a 10 times greater concentration between here and here. Otherwise, we might not see it. So this is one way of using what we've been using for advection to talk about salt concentrations, and then how I just wanted to show you how you can take something that's very easy to measure, like electrical conductivity, change it into a salt concentration, and then estimate how much salt you would need to be putting in.